Welcome to the History of Simple Things, where we delve into the fascinating history behind the little things that shape our world. In today's fast-paced world, batteries power everything from our smartphones to electric cars. But have you ever wondered how these essential power sources are made? Join us on a journey through time as we explore the fascinating history of battery manufacturing. The story of batteries begins thousands of years ago, with ancient civilizations experimenting with electrochemical cells. The Baghdad battery, discovered in Iraq, dates back to the Parthian period and is believed to be one of the earliest examples of a battery-like device. It consists of a clay jar containing a copper cylinder and an iron rod. Inside the jar, researchers discovered evidence of an acidic substance, such as vinegar or wine, which could have served as an electrolyte. The theory behind the Baghdad battery is that it could have been used as a primitive form of battery to generate a small electric current. When the copper cylinder and iron rod come into contact with the electrolyte, they create a simple electrochemical cell. Similarly, Alessandro Volta's invention of the voltaic pile in the late 18th century paved the way for modern battery technology. It consists of alternating discs of zinc and copper separated by layers of cardboard or felt soaked in an electrolyte solution, such as salt water or sulfuric acid. The discs are arranged in a stack, with each zinc disc connected to a copper disc through the electrolyte-soaked separator. When Volta constructed the first voltaic pile, he observed that it produced a continuous electric current. This discovery challenged the prevailing belief that electricity could only be produced by chemical reactions involving separate bodies of metal and electrolyte. The Industrial Revolution brought significant advancements in battery manufacturing. Lead-acid batteries, with their ability to store and release electricity through a reversible chemical reaction, became the standard for early electrical systems. These batteries were crucial for powering telecommunication networks, early automobiles, and even submarines. As the 20th century dawned, Thomas Edison's invention of the alkaline battery revolutionized portable power. Alkaline batteries offered higher energy density and longer lifespan compared to their lead-acid counterparts. With the advent of consumer electronics, such as radios and flashlights, alkaline batteries quickly became ubiquitous. The latter half of the 20th century witnessed the rise of rechargeable batteries, offering consumers a more sustainable and cost-effective power solution. Nickel-Cadmium batteries, introduced in the 1950s, were among the first commercially successful rechargeable batteries. However, concerns over cadmium's environmental impact led to the development of safer alternatives. In the 1990s, the emergence of lithium-ion batteries marked a significant milestone in battery technology. These lightweight, high-energy density batteries became the go-to choice for powering everything from laptops to electric vehicles. Now, let's take a closer look at how lithium-ion batteries, one of the most prevalent battery types today, are manufactured. The process begins with the production of electrode materials. Graphite is used for the anode, while lithium cobalt oxide, lithium iron phosphate, or other lithium compounds are used for the cathode. These materials are mixed with binders and solvents to create a slurry, which is then coated onto metal foils. Precision coating machines ensure uniform thickness and distribution of the electrode materials. Next, the coated foils are passed through a drying process to remove excess solvents, leaving behind thin electrode layers. These electrodes are then cut into precise shapes and assembled into battery cells, along with separators and electrolyte solutions. Assembly lines carefully integrate these components, with each step monitored for quality control and consistency. Once assembled, the cells undergo testing to ensure they meet performance and safety standards. Testing facilities simulate real-world conditions, subjecting batteries to temperature extremes, mechanical stress, and overcharging scenarios to evaluate their durability and safety. From raw materials to finished products, the manufacturing of batteries involves a complex, yet meticulously orchestrated process. As we look ahead, innovations in battery manufacturing will continue to drive advancements in technology, powering the devices and vehicles that shape our world. The journey through the history of battery manufacturing reveals a remarkable tale of human ingenuity, innovation, and perseverance. From the ancient experiments with electrochemical cells to the sophisticated production processes of modern lithium-ion batteries, each era has contributed to shaping the evolution of battery technology. The earliest attempts at harnessing electricity, exemplified by artifacts like the Baghdad battery and the Voltaic pile, laid the foundation for the exploration of electrochemistry. These early pioneers, driven by curiosity and a thirst for knowledge, paved the way for future discoveries that would revolutionize the way we power our world. The Industrial Revolution brought about significant advancements in battery manufacturing, with the widespread adoption of lead-acid batteries powering the burgeoning electrical systems of the time. These robust batteries played a crucial role in electrifying industries, transportation, and communication networks, laying the groundwork for the modern age of technology. The 20th century witnessed a rapid expansion in the variety and accessibility of battery technologies. From the advent of alkaline batteries, which provided portable power for a myriad of consumer devices, to the development of rechargeable batteries like nickel-cadmium and lithium-ion, which offered greater efficiency and sustainability. Each innovation fueled the growth of industries and transformed the way we live and work. Today, the manufacturing of batteries has become a highly sophisticated process, characterized by precision engineering, advanced materials science, and stringent quality control measures. State-of-the-art facilities employ cutting-edge technologies to produce batteries with higher energy density, longer lifespan, and improved safety profiles. Looking ahead, the future of battery manufacturing holds immense promise and potential. Breakthroughs in materials science, such as the development of solid-state batteries and next-generation electrode materials, offer the prospect of even higher performance and energy density. Furthermore, advancements in manufacturing processes, automation, and digitalization are poised to further enhance efficiency and reduce costs. In essence, the history of battery manufacturing is a testament to human creativity, resilience, and adaptability. From ancient civilizations tinkering with clay jars and metal rods to modern-day engineers pushing the boundaries of electrochemistry in state-of-the-art laboratories, the quest for better batteries continues to drive progress and innovation. As we embark on the next chapter of this journey, one thing remains certain: the power of batteries will continue to shape the world we live in, powering our devices, fueling our industries, and propelling us towards a more sustainable future. Thank you for joining us on this journey through the history and manufacturing of batteries. We hope you gained valuable insights into the evolution of this essential technology and its profound impact on our daily lives. Where we explore the latest in technology and innovation. Today, we're diving into the world of rechargeable batteries, from the classic nickel-cadmium to the ever-popular nickel-metal hydride, the advanced lithium-ion batteries, and some exciting new emerging technologies. Let's get started. First up, we have the nickel-cadmium, or NiCad batteries. These were among the first rechargeable batteries available for consumer electronics. But how do they work? NiCad batteries consist of a nickel oxide hydroxide positive electrode, cathode, and a cadmium negative electrode, anode, with an alkaline electrolyte, typically potassium hydroxide. During discharge, the cadmium anode releases electrons, which travel through the external circuit to the nickel oxide hydroxide cathode, where they are accepted. This flow of electrons generates the electrical current we use. Nickel batteries are known for their robustness and ability to deliver a high discharge rate, making them ideal for power tools and emergency lighting. However, they have a major drawback: the memory effect. This phenomenon occurs when the battery is not fully discharged before recharging, leading to a reduced capacity over time. Additionally, Nickel batteries contain toxic cadmium, posing environmental and disposal challenges. Next, we have Nickel-Metal Hydride, or NiMH batteries. These emerged as an improved alternative to Nickel batteries in the late 20th century. The working principle of NiMH batteries is quite similar to that of Nickel batteries. They also use a nickel oxide hydroxide cathode, but the anode is a hydrogen-absorbing alloy instead of cadmium. When discharging, the hydrogen atoms in the anode release electrons, generating an electric current. The nickel oxide hydroxide cathode accepts these electrons, completing the circuit. NiMH batteries offer a higher energy density, meaning they can store more energy in the same amount of space. They are also less prone to the memory effect, making them more user-friendly. Furthermore, NiMH batteries are more environmentally friendly since they do not contain toxic heavy metals like cadmium. These qualities make NiMH batteries a popular choice for devices such as digital cameras, handheld gaming consoles, and hybrid vehicles. However, they do have a higher self-discharge rate compared to other types of rechargeable batteries. Now, let's talk about lithium-ion, or Li-ion batteries. These have become the gold standard for portable electronics, from smartphones and laptops to electric vehicles. But what makes them so special? Li-ion batteries operate using a lithium cobalt oxide cathode and a carbon-based anode, typically graphite, with a lithium salt electrolyte. During discharge, lithium ions move from the anode to the cathode through the electrolyte, while electrons flow through the external circuit, providing electrical power. During charging, the process reverses, with lithium ions moving back to the anode. Li-ion batteries boast an excellent energy density, allowing for longer use between charges. They also have a low self-discharge rate and no memory effect, which means you can charge them whenever convenient without worrying about capacity loss. One of the most significant advantages of Li-ion batteries is their lightweight and compact design, which is crucial for modern portable electronics. However, they are not without their issues. Li-ion batteries can be sensitive to high temperatures and require sophisticated battery management systems to ensure safety and longevity. Despite these challenges, their benefits far outweigh the drawbacks, making them indispensable in today's tech-driven world. Finally, let's look at some emerging technologies that promise to revolutionize the battery industry. One such technology is the solid-state battery. Unlike traditional batteries that use liquid or gel electrolytes, solid-state batteries use solid electrolytes, which offer several advantages. They are safer, as they eliminate the risk of leakage and reduce the likelihood of thermal runaway, which can lead to fires. Solid-state batteries also have the potential for even higher energy densities, longer lifespans, and faster charging times. Researchers are also exploring other innovative materials and designs, such as lithium-sulfur and lithium-air batteries, which could further enhance performance and sustainability. Additionally, advancements in supercapacitors and graphene-based batteries are being closely watched as they promise ultra-fast charging and extended cycle life. The world of rechargeable batteries has come a long way from the early days of nickel-cadmium to the advanced technologies we have today. Each type of battery has played a crucial role in shaping the landscape of portable power. Nickel batteries laid the foundation with their robustness and high discharge rates despite their environmental drawbacks and memory effect issues. NiMH batteries improved upon this foundation by offering higher energy density and being more environmentally friendly, though they still face challenges with self-discharge rates. Lithium-ion batteries revolutionized the industry with their superior energy density, lightweight design, and minimal memory effect, making them the go-to choice for a wide range of applications from smartphones to electric vehicles. However, they require careful management to prevent issues like overheating and capacity loss over time. Looking forward, the future of battery technology is incredibly exciting. Solid-state batteries promise to address many of the safety and performance issues associated with current battery technologies by using solid electrolytes. This could lead to batteries with even higher energy densities, longer lifespans, and faster charging times. Additionally, the exploration of lithium-sulfur and lithium-air batteries holds potential for even more significant advancements in energy storage capacity and sustainability. Innovations in supercapacitors and graphene-based batteries are also on the horizon, offering the possibility of ultra-fast charging and extended cycle life, which could revolutionize everything from consumer electronics to renewable energy storage. As technology continues to advance, the development of new materials and designs will likely lead to even more efficient and environmentally friendly batteries. These advancements will not only power our gadgets and vehicles, but also play a critical role in addressing global energy challenges, such as the integration of renewable energy sources and the reduction of carbon emissions. Thank you for joining us on this journey through the evolution of rechargeable batteries. We hope you found this information insightful and useful. Today, we're diving into the fascinating world of automotive storage batteries. These essential components power our vehicles, ensuring we can start our engines and run our car electronics efficiently. But have you ever wondered how these batteries are made? From raw materials to the final product, the process is a blend of chemistry, engineering, and precision manufacturing. So let's take a detailed journey through the entire production process of automotive storage batteries. The journey of automotive storage batteries began in the 19th century. In 1859, the French physicist Gaston Plante invented the first rechargeable battery, which was based on lead-acid chemistry. This innovation laid the groundwork for the development of automotive batteries. The early 20th century saw the widespread adoption of these batteries in cars, particularly with the introduction of electric starters in Cadillac vehicles in 1912. Prior to this, cars were started with hand cranks, a laborious and sometimes dangerous task. The convenience and reliability of lead-acid batteries quickly made them a standard in the automotive industry. As technology advanced, so did the batteries. The 1970s brought about the advent of sealed lead-acid batteries, which required less maintenance and were safer. Fast forward to the 21st century, and the rise of electric and hybrid vehicles has pushed the development of more sophisticated battery technologies, such as lithium-ion batteries, which offer higher energy densities and longer lifespans. The production of an automotive storage battery begins with the raw materials. The primary materials used are lead, acid, and a plastic case. Lead is a critical element, used in both the positive and negative plates of the battery. This lead is often sourced from recycled batteries, making the process more sustainable. The lead is melted down and purified in large furnaces, ensuring any impurities are removed. Meanwhile, the plastic cases are typically made from polypropylene, chosen for its durability and resistance to battery acid. These cases are molded into specific shapes and sizes to fit various vehicle requirements. Next, we move on to the manufacturing of the battery plates. The purified lead is alloyed with other metals like calcium, tin, or antimony to improve the battery's performance and lifespan. This alloy is then cast into grids, which will form the framework of the battery plates. The grids are then pasted with a mixture of lead oxide and sulfuric acid, forming what is known as the active material. This process is meticulously controlled to ensure the paste adheres properly to the grids, which is crucial for the battery's efficiency and longevity. After the plates are prepared, they are assembled into cells. A typical automotive battery consists of 6 cells, each producing around 2.1 volts. The positive and negative plates are alternated within each cell, separated by insulators known as separators. These separators are usually made from a porous material like rubber or glass fiber, allowing the ionic flow while preventing electrical contact between the plates. The assembled cells are then placed into the battery case, and the cells are connected in series to achieve the desired voltage. The next critical step is filling the battery with sulfuric acid, which acts as the electrolyte. This acid filling must be done with extreme care, as sulfuric acid is highly corrosive. The filled battery is then subjected to an initial charging process known as formation. During this stage, the battery is connected to a charging system that slowly applies a controlled current, causing chemical reactions within the cells that form the active material on the plates. This formation process is crucial for activating the battery and ensuring it can hold and deliver charge effectively. Once the formation process is complete, the battery is sealed to prevent leakage and protect the internal components. The sealing is typically done using a heat sealing process that fuses the lid to the case, creating a secure and leak-proof battery. After sealing, each battery undergoes rigorous quality control tests. These tests include checking the voltage, capacity, and overall performance to ensure each unit meets the required standards. Any battery that fails these tests is rejected and sent back for reprocessing. The final step in the manufacturing process is the labeling and packaging of the batteries. Labels are applied to each battery, providing essential information such as the type, voltage, and manufacturing date. The batteries are then packaged and prepared for distribution. They are shipped to various distributors, car manufacturers, and retailers, eventually finding their way into the vehicles we drive every day. And that's how automotive storage batteries are made. From raw materials to the final product, the process is a complex and fascinating blend of science and engineering. These batteries are the unsung heroes of our vehicles, providing the power needed to start the engine and run the electronics. The history of automotive storage batteries is a story of continuous innovation and adaptation. From the early lead-acid batteries that powered the first electric cars to the advanced lithium-ion batteries driving today's electric vehicles, each advancement has played a crucial role in shaping the automotive industry. As we look to the future, the ongoing evolution of battery technology promises to unlock new possibilities and drive further progress in the world of transportation. Thank you for joining us in this journey, and we hope you enjoyed this deep dive into the world of battery manufacturing. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.